Last time we introduced Gauss's law, which states that the total flux that passes through any closed surface is proportional to the electric charge enclosed by that surface. It is common to refer to this closed surface, through which the flux is calculated, as the Gaussian surface. We demonstrated the validity of Gauss's law by explicitly calculating the flux through some Gaussian surfaces and finding that it was indeed proportional to the charge enclosed. Today, we will use Gauss's law to calculate the electric fields produced by some special charge distributions. In general, using Gauss's law to determine the electric field is extremely difficult, since the electric field occurs inside the integral in Gauss's law. For example, here we see the electric dipole that we introduced last time. If we attempt to use a sphere centered on the dipole as a Gaussian surface, for example, we see that the magnitude of the field is not constant on the surface. For example, it decreases as we move away from the axis of the dipole. And the direction of the field is also not constant. For example, it is perpendicular to the surface along the axis and becomes more parallel to the surface as we move away. Consequently, there is no easy way to evaluate E dot dA at all points on the surface in such a way that we can move E outside the integral, which would be necessary if we are to solve for E. On the other hand, if we replace the dipole by a single point charge as shown, we have a completely different situation. Here, the electric field is constant at all points on the surface of the sphere, and its direction is always perpendicular to the surface. Consequently, E dot dA is just equal to E times dA at all points, and we can take E outside of the integral and solve for it. In general, for cases with a high degree of symmetry, it is possible to choose a Gaussian surface such that the electric field can be pulled outside of the integral. For example, if we can choose a surface such that the electric field has a constant magnitude at all points on the surface and is always perpendicular to the surface, as in the case of the point charge at the center of a Gaussian sphere, then we can move the constant field outside the integral and solve for it. There are three such symmetries for which this is useful, corresponding to our three spatial dimensions. We have the full three-dimensional symmetry of the sphere, the two-dimensional symmetry of the infinite cylinder, and the one-dimensional symmetry of the infinite plane. In each of these cases, we can construct Gaussian surfaces that allow us to solve for the electric field by pulling it outside of the integral. We'll begin by looking at an example of spherical symmetry on the next slide.